Afternoon, everyone. So, in the last lecture, we were talking about two algorithms we have seen. One with respect to discrete perceptrons, but it was a layer. The algorithms that we saw worked over a layer of neurons. Okay? Um, we just summarized the learning rules and we talked about these two algorithms. The first one mm, was not named as such, but we solved a problem based on that. That is the R category discrete perceptron training algorithm. It is R category. That means multiple categories. Okay. You will find these algorithms in the textbook which you have, that is Zurada. Both of these algorithms are present in that textbook. Okay. So what we these algorithms actually work over a layer of neurons because you just extend the original algorithm, the learning rule that you have studied, that is perceptron learning rule, which was for a single neuron. You are extending it to a layer of neurons. It's a single layer network. So this is the input layer, and a single layer of neurons was used as part of these algorithms. Okay. And second algorithm, the same concept, the delta, instead of perceptron learning rule, you have the delta learning rule, which is extended, okay, over a layer of neurons. So the type of activation function differs there. So you're using the delta learning rule here. Here you're using the perceptron learning. So this is perceptron. This is delta. Okay. Delta perceptron extended, delta extended. Again, this was known as multi-category. It's the same. It's multi-category because you have, if you want to classify into multiple categories, a single neuron will not do. You require n neurons. Depends on how many categories you have. It was continuous perceptron training algorithm. Continuous perceptron is nothing but delta. So these were the two algorithms that we discussed in the last lecture, and we will move ahead now. So we started from a very basic uh, single neuron network. Then we move to a single layer of neurons in the output layer. And then we will extend this concept further today. And we will construct networks where there will be more than one layer. So we will introduce a concept of a hidden layer. Okay. So today's discussion is as follows. We'll be looking at multi-layered feed-forward networks, and the learning rule, the delta learning rule actually is generalized so that uh, the weight update can be done for the hidden layer as well. So the delta learning rule extended to a layer of neurons is fine because we are talking about only a single output layer. Okay? But these updates, whichever we are making to the output layers, actually need to be taken care of in the hidden layers as well, because uh, the errors which are introduced, they need to be back propagated back in the backward direction. That is what we need to do in order to train a multi-layered feed-forward network, and that is why we derive the equation of a generalized delta learning. Okay? So we generalize the delta learning rule to n number of hidden layers. So we will prove it for one hidden layer, and the same can be used for an n layered hidden layered network. Okay? And then we will look at the error backpropagation training algorithm, EBPTA, also, which uses the generalized delta learning rule, which is used for training a multi-layered feed-forward network. So what is a multi-layered feed-forward network? A multi-layered feed-forward network is simply an interconnection in a feed-forward fashion. Okay? So then you have multiple layers of computational units or neurons, in other words, which are interconnected in a feed-forward fashion. Okay, and each neuron in one layer has directed connections to the neurons of the subsequent layer. So the connections flow in only the forward direction, right? Um, We know that a single layer neural network can solve only linearly separable problems. So the problem with a single layer network is that you cannot solve real world problems which are non-linearly separable. So that is why you need to introduce hidden layers. And that is where multi-layered feed-forward networks come into picture. Okay? So multi-layered feed-forward networks, they use delta learning rule in the supervised learning mode. So obviously they're supervised. Whatever networks we are talking about, they're supervised. So they're using delta learning rule. Okay? But let us see how this delta learning rule is applied to a multi-layered feed-forward network in order to update the weight. Because see, the primary goal of training is to adjust the weight so that the patterns are correctly classified. So the ultimate aim is you need to update the weights. You need a rule for updating the weights. That is the idea behind training of neural networks. Okay? So let us look at the generalized delta learning rule first. So let us consider this simple feed-forward network where you have a single layer of a hidden layer which is introduced in between the input layer and the output layer. So you have the input layer and you introduce a layer of a single layer of neurons between the input layer and the output layer. Okay. There are some notations that we are using for this particular network. Okay. So as you see, all the neurons that are there, they are continuous in nature. So each neuron is continuous in nature. Okay. And this, the output layer is called, this is the output layer, right? This is called K, this is called K. So there are K neurons in the output layer. Okay. And this is the hidden layer. There are J neurons in the hidden layer. Okay. So, and I is the dimensionality of the inputs. Okay. Now, whenever we are talking about all of these dimensions, I, J, K, just remember that whenever you have your input, it is always augmented. Whenever you're going for delta or perceptron learning rule, the input pattern is always augmented. And when we actually extend it further to a layered network, you have one extra neuron added everywhere. So there is a dummy neuron added here, okay, except for the last layer. Okay? Because the last layer is the number of classes. Last layer is the number of classes. Okay? In the hidden layers, you have this dummy extra neuron which is added, which will act as a bias for the for the subsequent layers that we have. Right? So you introduce one bias input here, you introduce one extra neuron here, okay, and wherever there are hidden layers. But now, for now, we are considering only one hidden layer, just as far as the derivation is concerned. Okay. Now, W, there are two sets of weights because there is one set of weights which is connecting the inputs to the hidden layer, and the second set of weights is connecting the hidden layer neurons to the output layer. Okay. So W are the weights which are connecting hidden to output, and V are the weights which are connecting the input layer to the hidden layer. Okay. So this is the network architecture that we are looking at for our derivation. So now we will derive the expression for the weight update. Now weight update has to be done for each of the set of weights. So W as well as, so you have two weight matrices. You have V and you have W, right? V is between input to hidden and W is from hidden to output. That is how it goes. Right? So you have to update both the weights. Okay? But we already know how to update the final layer weights. We already know how to update the final layer weights, because if we have a single layer of neurons, we know the algorithm to update these weights, and that is nothing but MCPTA, right? The delta learning rule extended to a layer of neurons in the output layer. We already know this equation. But we do not have an equation for updating the weights. The same equation, in fact, cannot be directly applied to update the weights of the hidden layer. Okay? So let us see what is the weight update for the hidden layer. Okay? So consider that we are doing it for a single weight. We are doing the update for a single weight increment or weight update for a single weight, delta Vji. Okay, so it's ijk, right? I is input, j is hidden, and k is output. So delta Vji are the weights which are representing input to hidden, I to j. If you recollect, the notation is that we had used. Also, I had talked about this notation when I was talking about MCPTA, that you have first ji, first you have j, then you have I. It's just a notation. What so j is the output for this, and I is the input, right? So output input, the convention that is used is output input. Delta Vji is output input, right? So when you use the gradient descent formula for the hidden layer, it is something like this, because you have to minimize the error. So ultimate aim is to minimize the error. E that we are looking at is the squared error, that is d half of d minus o the whole square. Okay, so this is the gradient descent formula, that is minus eta times dou by dou Vji of E, right, for all j's and i's. Okay. Now what we need to do is we need to actually do something so that we do this derivation. We compute the or we come up with an equation for this particular term. Okay, so what is this delta E? So dou E by dou Vji. If you use chain rule, you can introduce net j into this equation by writing it in this form. So dou E by dou net j times dou net j by dou Vji. Okay, so we are just introducing that. Why do we need to introduce that net j term here? Because you cannot find the derivative of E with respect to Vji directly, because E is using d minus o, okay, which is of the output layer. For the output layer, o is a vector which represents the output layer, and v is something which is from input to hidden. Okay, so what we need to do is we need to introduce keep on using the chain rule so that we can take derivatives and come up with the expression. So dou E by dou net j times dou net j time by dou Vji. So this is the equation. Now, if you look at this equation closely, the second term that we have here, this term that we have here, I can write net j as Vji times Zi. Because what is net actually? It is W transpose X, right? Weight times input, weighted sum of inputs, right? So in this case, it's net j. Net j means what? Net j is the weighted sum of inputs from input to hidden layer, right? So the vector for representing input was z. Input vector was z. If you see, look at this diagram. This is the input vector z. Okay, this vector, intermediate vector is y, and the final vector is o. Z, y, o. So this net j is nothing but the weights of that layer which connect input to hidden. Are you getting it? Input to hidden, those weights, that is v, those set of weights, that is v times z, that is net j. Okay. So if we substitute this right hand side, this in this equation, what will we get? We will get the value as Zi. This term will become Zi. this term will become Zi. Okay, because dou Vji with respect to Vji is nothing but 1, and that multiplied by Zi. So this term is Zi. And if we look at this particular term we will evaluate. Okay, so this the second term is equal to Zi, and the first term what we will do is we'll represent it by an error signal, a notation delta Yj. Let us call it the error signal between uh, the input and the hidden layer. Okay? So input and the hidden layer. So let us call it as delta Yj. So now this error signal term we have substituted as this. Delta Yj is nothing but minus of dou E by dou net J. We have just substituted this into the very first equation that we had, that is of delta Vji. So what was delta Vji? Delta Vgi is minus eta times this. This term we have used chain rule, we got this part as Zi, and so what we did is delta Yj is nothing but minus of this term. Okay, so once we substitute this in this equation of delta Vji, what do we get? We get eta times delta Yj times Zi. We get eta times delta Yj times Zi. Okay. So now we have updated that for very first equation that we had written. Now our task is to still compute this particular term, that is minus dou E by dou net J. This calculation is still remaining. Okay. So again, we use chain rule and we introduce Yj into this equation. So, so we are just introducing Yj into dou Yj into this equation. So by using chain rule, dou E by dou Yj into dou Yj by dou net J. Okay, minus sign was there, so that remains as it is. Now this, look at the right hand side of this equation. The right hand side of this equation has two terms. This is the first term, this is the second term, and there's a minus sign. Just ignore it for now. So looking at the first term, for the first term, let us replace this E error signal with its actual equation, that is half d minus o the whole square. Now it's summation of all the error signals error signals for all the neurons. Okay. So there are k neurons in the output layer. You sum up all the squared errors for each of the neurons that you have. So summation of that, right? So dk minus ok. Ok is nothing but f of net. F of net is nothing but the output. Output is nothing but f of net. Okay, so that is how you get this. And the right term, the second term that you have in this equation, it is nothing but f dash net j. So because y is nothing but f of net, yj is nothing but f of net, and because y is the output, so you have z followed by y followed by o. Okay, z is the input, y is the output of the hidden layer. So what is y? It is f of net j. Okay. O is the output of the network final layer. O is the output of the output layer, which will be f of net k. Okay. Because net, we are just distinguishing it, the two net values, by using k and j, because k represents the output layer neurons, j represents the hidden layer neurons. Okay. So, so when you substitute this y as f of net, you will get this term reduces to f dash of net. Okay. F dash net. So this term is nothing but f dash net in this equation. Okay. And we have just substituted the equation for expression for E into this, okay, and just expanded it. So these two things we have done. Now after this, We'll try to simplify it further. Let us take the summation outside. From that equation, let us take the summation outside and find the derivative of that term. What we're going to do is we're going to take the summation outside, find the derivative of this, apply dou by dou yj over this particular equation. Okay. So this is 2 times d minus o, right? Derivative of this. What is derivative of this with respect to y? 2 times d minus o. So 2 and this 2 and that 2 gets cancelled, times f dash times d dou by dou yj of this particular f of net y. Okay. So just a minute. This particular equation, we have written it as, we have found out the derivative, taking the summation outside, found out the derivative. Okay. D minus O times dou by dou yj of f of net. Now, if you find out the derivative, it will be f dash of net k times dou by dou y of net k. Okay. So, further simplifying this, the derivative is further reduced. Simplify. And this term that we have here, d minus o times f dash net, this term that we have in this equation is nothing but delta OK. Delta OK are the error signals for the output layer. Output layer, this term, if you recollect, we had derived this equation earlier for the output layer. Okay, that is d minus o times f dash net. D minus o times f dash net, if you recollect. Okay, let us call it as delta OK. Let us call the error term for the output layer as delta OK. Okay. So, and this term in the equation, is nothing but WKJ. Why? Because net, again you substitute net. What is net? W transpose X, but it is net K. So the weights for that layer are W weights, WKJ, right? Other weights, individual weights, times the input, right? Weighted sum of inputs. What is net? Weighted sum of inputs. What is the input for this layer? It is Y. The input for this layer, right? There are 3 layers, I mean 2 layers, talk in terms of neurons only. To include the input layer, then there are 3. Going back to this. Okay. So for this layer, the input, what is the input? Y. Right? If I want to compute the net for this, a neuron in this layer, what will be the net for the neuron in this layer? Suppose this is a neuron which I want to consider, and I want to find the net value for it. It will be this W times Y, because Y, which is the output of the hidden layer, is the input for the output layer. Confusing? Y, which is the output of the hidden layer, is the input for the output layer. Right? So you just have to multiply W with Y. So once you substitute that net K as W times Y, you further simplify that equation. Further simplify that equation, and the derivative of this will be 1. Y with respect to Y will be 1. Times this WKJ you take outside. Okay. So this term actually equals to WKJ. Okay. So what you have got is minus of summation of delta OK times WKJ. Okay. This is what is the expression for dou E by dou Y. Minus of summation of delta OK times WKJ. Okay. Now all these expressions that we have derived, we will just substitute them in the original equation that we have. Okay, so delta yj, the term we were trying to compute, that error signal between the input and the hidden layer, right? That we're trying to compute. So that becomes so 5, 7, and 12. So I've just labeled the equations which where we are substituting. So this was a term actually in one of the equations. Okay, so this term we have substituted, del dou e by dou yj was a term in one of the equations where we have substituted this value, this term, this expression into that equation. Okay, so I'll just go back to 5, 7. What is 5, 7? So 5 was this, 7 we had derived it as f dash of net. So this second term is f dash of net, and for this particular term we have computed as summation w times um, delta. Okay, okay, delta y, delta. Okay, yeah, the expression that we just derived. So minus of, so minus into minus becomes plus. Okay, so it is simply summation of w and delta times f dash net. That is what we have got. So f dash net, that minus sign goes off, f dash net times this term. Okay. So delta yj we will substitute in that equation 3, very first equation which we had written, that is for delta vji, the weight adjustment, the weight increment equation. So that becomes now eta times f dash net. This was delta yj, this term we were trying to compute. It was eta times delta yj, right? Delta yj. So it becomes eta times f dash net j times zi, the input. It was eta times delta yj times zi. This was the equation. Okay, this was the equation. Into this equation, we are just substituting these values. So delta yj is this. We have substituted it here. So we have got it as eta times f dash net times zi times this. Okay, just putting the summation towards the end. That is what we are doing, rearranging this. Okay. So now this equation that we just saw for delta vji, it is called as the generalized delta learning rule. That equation is called as a generalized delta learning rule, which is used to update the weights of the hidden layer. Any hidden layer that you have, you make use of this weight update equation. Okay. And so using this weight update, we know that vj, the new weights, vji dash, this is, consider this as the new weights to be computed, will be the old weights vji plus delta vji. This is delta vji, right? This term is delta vji. We substitute in this equation, you get this expression. Okay. So this is the expression for delta learning rule, generalized delta learning rule for updating weights of the hidden layer. Okay. So if you visualize this in the vector notation, then V is the weight matrix, which is for the hidden layers, input to hidden layer matrix V. Okay. So V is equal to V plus eta times delta Y times Z transpose. Now this is in vector form. The previous equation that we saw was a single weight adjustment. For that vector, each of the individual weights, how it is being updated. Only thing is we are rewriting it in vector. Okay. So this, it's eta times, eta is the learning rate, Z is the input to this, right? Z is the input to the hidden layer. And this is the learning signal. Learning signal for the hidden layer is delta Y. It's a vector now, it's a vector. It is what we have got earlier, W times delta O times F dash Y, okay, in vector form. And F dash Y, we know if we are going to use these activation functions that we have, either bipolar or unipolar, if you're using bipolar, just substitute it as half 1 minus y square. If you're using unipolar, it will be y into 1 minus y. Remember, it is y because the output of the hidden layer is y. So far, we were looking at O, O, O every time because O was the output of the output layer. So y is the output of the hidden layer. So it is half 1 minus y square. If you're using bipolar continuous, if you're using unipolar continuous, it is y into 1 minus y. Okay. Now this generalized delta learning rule is the learning rule which you are going to use for updating the weights of the hidden layer. And this is a part of the error backpropagation training algorithm, that is EBPTA. Okay. So to understand this algorithm, we have just derived the expression for the layers. So we know the output layer expression, we already know. We have done it. It's the normal delta learning rule for an output layer. We have extended that to derive the expression for weight update for hidden layers. So those weight updates we just have to uh, um, introduce in the error backpropagation training algorithm. So let us look at the architecture again. It's the same architecture. So this was the architecture we were looking at few slides back, the same architecture. Single hidden layer, single output layer, and the input layer that you have. Okay. So when we talk about the algorithm, with respect to the algorithm, how the training of this network takes place, it takes place in two phases. Okay. The first phase is known as the feed-forward recall phase, and the second phase is known as the feedback phase. Okay. Or feedback error propagation phase rather. Okay. So there are two phases in which this algorithm works. First is the feed-forward recall phase, and second is the feedback error propagation phase. Okay. So let us see how these phases work in the form of this block diagram. So there are two parts to this diagram. So the feed forward phase is shown in the form of the arrows which are shaded in gray. So the gray arrows are representing the feed forward phase. Okay, and whatever is not shaded, that is the feedback phase. Okay? So how does this algorithm work? The same architecture that we saw in the form of the neurons, now we have just replaced those neurons in the form of blocks. Okay. Now these blocks that we have here, one by one we will see. So first is the input vector that is given, that is Z. Z is the input vector that is given. And the set of weights which are connecting the input to the hidden layer. So this is the hidden layer. Okay. Those weights are known as V. Right? They are represented by V. Okay. So the first step is to compute net. Any kind of problem solving that you have done, what do you do first? You compute net, right? V times Z, because V are the weights and Z is the input, right? So you compute net J. Okay. First input pattern is given to you. Take that input pattern, multiply it with the weight matrix, and get the net J. Get a vector called as net J. It's a vector of J values, right? So once you're getting this J values, what you do is each of these J values you pass over an activation function. So you have these J neurons which are there. So it's a layer of neurons. Okay. So you have these J net values, you pass them over an activation function, through an activation function, that is this. So Y is nothing but the output of the hidden layer. Y is the output of the hidden layer. So you apply the activation function, any of the continuous activation functions you can apply, and you get the output of this hidden layer. Okay. So this is a nonlinear mapping which is applied to the net values. So now that you have this vector Y, which is the output of the hidden layer, you take this Y and next you have another set of weights, that is W. So the second weight matrix, that is W, you multiply with this vector Y of outputs which you have computed for the hidden layer. Okay. You compute these net values now. These net values are represented as net K. Okay, because you will get K such values because there are K neurons in the output. Okay. So now these K values that you have, each of these K values that you have, you need to pass them through an activation function. So you pass each of these net values through an activation function that you're using in the output layer. Okay, that is nonlinear mapping of net K. This is the activation function. So this will give you the output of the network. This is the final output. So this is going to give you the output of the network O. So you will get one more vector at the end, that is a vector of output values. Okay. So this whatever these steps that we have seen so far is nothing but the first phase. So this forward propagation is the first phase. This is the phase 1. It is simply computation of the activation values. Compute net, find the activation, compute net, find the activation. Okay. You keep on doing this in the forward direction. Okay. This is phase 1 of the error backpropagation training algorithm. Now the second phase that we have is phase 2, that is error calculation, right? And backpropagate the error. That is what you're going to do. So phase 2 is represented by this lower half, you can see the diagram. Phase 2. Okay. Phase 2, what happens is, whatever equations that we have derived so far, we will be using. So we have D with us, the label. D minus O is computed because we need to update the weights, right? So to update the weights, what do we do? So for updating the weights, first we will start with the output layer weights because we do not have any dependency here. We already know that delta W is directly, we have the equation using delta learning rule. It is eta times learning signal times the input. Eta times delta, this is the learning signal R, times the input, right? Input to this layer is Y, right? It is Z, Y, O. So input to the output layer is nothing but Y. Input to the output layer is nothing but Y. So eta times delta, we represented by delta O times Y, right? So this is the equation for weight update. This delta O is nothing but D minus O times F dash net, if you recall it. It is D minus O times F dash net. Delta learning rule, D minus O times F dash net. It's eta times D minus O times F dash net times input, that is Y, the weight update. Okay. Once you have this, okay, you have these terms, delta W terms. This, what do? You compute the weights W. Okay. And using these W terms that you have, actually, these weights you multiply with the error signals. So these error signals are going to be useful to you. These error signals, it's a vector of errors that you have. These error signals are going to multiply with the weights W. If you remember, it was summation delta OK times WKJ, okay, which was used as part of the equation in the hidden layer. Okay. So you require, these error signals are required in the hidden layer. The error signals that are computed as part of the output layer are required in the computation of error signals for the hidden layer, right? So you need to compute this first. When you're backpropagating, the very first error signals that you compute will be of the final layer, the output layer. Once you get this, using this, you will substitute in this equation, that the equation for computing the error signals for hidden layer, the previous layer. Okay. So it will be summation of this times this you multiply, if you're talking at the individual weight level, and then multiply it with the derivative f dash net, f dash of net for this. So it is net j. Okay. Here you will be using f dash net of k. This will be f dash net of j. Okay. So what you're going to do? You will multiply this term with f dash net, and you will get the error signal here, this delta y. So eta times delta yj times the input will be the weight update for the input to hidden layer. So delta will same terminology. Eta times the error signal times the input to that. Input to this layer. Input to this layer is what? Input to the hidden layer is what? It is nothing but z. Z is the very first vector that you're giving, right? Z to y to o. Z is the input to the hidden layer. So this time you're going to use z in the computation. So eta times delta y times z. Delta y is the same thing, the equation that we have used, generalized delta learning rule. You just you need the this layers, the next layers weight, the error signals here in the computation. That is why you need to compute this first, then only you can go ahead. Okay, assume that there was one more layer previous to this, there was one more hidden layer here. What would you have done? Using this, you will be multiplying using the same equations, sigma of delta y times whatever the, suppose those weights were u, will multiply with those weights. Are you getting the idea? Is everyone getting this idea? So in order to compute the error signals of the previous layers, you have to go from right to left. What's the output? Using the output error signals, you compute the previous hidden layer. And if there's one more hidden layer before that, you use those error signals from that hidden layer and go ahead towards the left, okay, till you reach the last hidden layer. That is how you update the weights. Okay. So this is the idea behind error backpropagation training algorithm. Okay. The same idea we have put it down in the form of an algorithm. Okay. For this single hidden layer we have put it down, you can extend it to multiple hidden layers like how I just explained. These are the usual notations you have for whatever algorithms we have written so far, SDPTA, SCPTA, MCPTA. These are the usual notations. Okay, we have added more layers, so according I, J, K, dimensionality is mentioned. Then choosing eta, choosing Emax, right, the error. You initialize the weights at small random values, and then you start your training. So step one is just initialization of all the parameters that you have, and then at step two you start the training. So just give the input. So there are two phases, right? First phase, what you're going to do is just compute the forward activation. So you compute y, you compute o, right? And you are also computing the cycle error, because cycle error that you're going to compute, you're going to use to stop the training. Emax you have chosen. So you're going to compute cycle error, and once it goes below Emax, you will stop the training. And then what you have here is you are computing the error signals delta O and delta Y. Delta OK is half D minus OK into 1 minus OK square. So we are assuming in this particular algorithm right now, the activation function that is being used is bipolar continuous. It is actually D minus O times F dash net. This term delta OK is D minus O times F dash net. F dash net is half 1 minus O square in case of continuous bipolar continuous, right? Similarly, delta Yj. Delta Yj is, again, we are using the derivative of F dash net, but net J is Y, output is Y for that layer. So it is half 1 minus Y square times that error signal which we had, the summation delta W, delta times W, right? And then what we do is we update the weights of this particular layer. So we update the weights of the output layer, that is delta eta times delta OK times Yj. that is delta W Aj. Okay. Similarly, you update the weights for the hidden weight. Delta W V Vji. Okay. So once this is done, what happens is, so this part is, up till this part is the first phase. This is, and this also could be assumed in the first phase. This is phase 1 and this is phase 2. We are computing the errors and we are back propagating. We are updating the weights. Okay. And then using this counter, you just check whether you are done with all the patterns. Once you are done with the patterns, check for the cycle error, whether it has reduced considerably. If yes, you stop the training. If not, you go for the next iteration. Okay. So this is the error backpropagation training algorithm. We'll be implementing this. You'll be implementing this as well, but we'll be using a library function. But a demo, I have just created a demo of this particular function. I'll give that to you. You can go through it for a simple problem. Okay. So what we'll do is, in the next lecture, we will just solve some problems based on this error backpropagation training algorithm on some simple networks, so that we understand it's working and we are very well versed with it. Okay, because you tend to forget it. So once you solve the problem, both the phases, feed forward and feedback, for one iteration or two iterations, you will come to know how it works. You'll be very confident with it. So we'll be having some problem solving on this in the next lecture. That's all for today. We'll stop here. Thank you.